Okay, so this is 17.3 conservative vector field. So let's just start out with the definition, and we'll immediately see why this is something that's important. So F, so this is a vector field, is conservative on a region. So this could be in 2 dimensions, in the plane. It could be in space. It could be in 4 dimensions, any dimensions. So on a region R, if there is a function phi, so if you're in the plane, the phi should be a 2-variable function. If you're in space, it should be a 3-variable function, etc. Defined on R, so that f is equal to gradient phi. All right. So you're conservative if you have a potential function, right? If you are the gradient field of a function. We said back when we introduced vector fields that this is really great. You always would like your vector fields to be conservative because, we didn't use conservative. You would like them to be gradient vector fields because gradient vector fields are much more easy to work with. We'll see a lot of why that is today, and we'll also see how to tell whether a vector field is conservative, and if it is conservative, how to find this function phi. All right, so there's actually going to be quite a bit of definitions today because there's a lot of conditions on our criterion for determining, for example, whether a vector field is conservative or how to find the potential function in the case which it is. So let's start with definitions. So let's start with a simple closed curve. So we kind of have looked at this already, but a simple closed curve is one where closed means it comes back on itself. So the endpoints are the same, right? So let's say we have a curve, looks like that, right? Closes up on itself and does not intersect itself, okay? So this is, let me put it like this, loop, and then simple means does not intersect itself. All right, so we'll be working with simple closed curves quite a bit, especially since boundaries of regions in R2, boundaries of regions in a plane are gonna be simple closed curves. All right, another definition. So I'm not gonna give kind of a careful mathematical definition here. You can take a look in the book if you do want one. Essentially, it says, at least I think our book says, something like if you parameterize the curve, there's no 2 times that have the same output, right, in the plane or in space or whatever is appropriate. Okay, the next one is connected, let me break it into 2 of them. So connected region. So the idea here is we're talking about a region. For example, I'm going to draw a picture in the plane, but this also works in space as well. A connected region is one where every point can reach every other point through a path, all right? Through a continuous path that doesn't break. So this one is a very straightforward definition. Something which is not a connected region is exactly what you would think. If I have something like this, this being my region, these 2 pieces, then this point can never reach that point. All right. So if a region is not connected, in a way, you don't really like it because what happens, the behavior of things in the first region is completely independent of the behavior of things in the second region. So they're a little bit harder to work with. So we really like connected regions. Okay, the third one is simply connected region. So this is a really important definition. First of all, we're talking about connected regions, so you can't have two pieces. Simply connected, there's a very careful mathematical definition, of course, for everything that we talk about. But for this, I think a good way to describe it is if you have a region that looks like this, a simply connected region is one where if you take any loop inside this region, right, any loop like this, you can slowly deform this loop so that it deforms into a point. All right. So what I mean by deform is you can, for example, shrink the loop. You can move it around, but you can't jump, right? You can't have sudden jumps. You can't break the loop or anything like that. All right. So for example, in this picture, if we start with this loop, for example, we can kind of slowly shrink it and shrink it and shrink it and shrink it till it just deforms into a point. All right. And for this particular region that I've drawn, any loop can be shrunken to a point. All right. Now, an example of a situation, so this would be called simply connected. This region is simply connected. Okay, so example of a region in R2 in the plane, which is not simply connected, would be a region like this that has a hole in it, right? So in this situation, you do have loops which can be shrunken to a point. For example, this loop right there, right? You can just make it smaller and smaller and smaller, and eventually it just becomes a point. No problem. However, if I look at this loop right there, that can never be shrunken to a point, right? Because if I try to shrink it, eventually it's going to hit this this hole, and it can never get through the hole, right? You're certainly not allowed to leave the region, right? For these situations, essentially the regions are going to be our entire world, right? Things aren't even going to be defined outside our region. When we work with vector fields on regions, it's very possible that there is no definition for the vector field outside the region. Okay, so as far as we're concerned, the world is the region. So you're certainly never allowed to leave the region. Okay, so you cannot shrink this loop without leaving the region or without breaking it so that it shrinks to a point, right? Because if you try to shrink it, right, eventually you're going to hit this barrier, which is the hole. Okay. All right, it always has to stay a loop. You cannot break it or anything like that. All right. So this is one example of not simply connected. And we're interested in this definition because what's going to happen is we're going to be able to tell information about vector fields being conservative or being able to find potentials for regions which are simply connected. All right. For regions which are not simply connected, there's complications. All right, so another picture of something which is not simply connected in the plane would be if I just take the entire plane and I just remove a single point. So let's say the origin. All right, so now my region is everything except the origin. So this is another example where it's not simply connected because that loop right there cannot be shrunken to a point. Because, well, eventually when you shrink it, right, you're going to hit this barrier, which is that hole. Even if that hole is just a single point, you cannot pass through that hole. All right? So this guy is not simply connected. And in many ways, mathematically, the two regions that I've drawn that are not simply connected are the same in some ways. Okay. Let me give an example in R3. So in R3, if I do, in space, if I do, let's say, a torus, I'm not even going to draw the axes. So a torus, so basically a donut, the inside of a donut, let's say, is not simply connected because you have actually two loops which cannot be or two kind of classes of loops which cannot be deformed away, right? So this loop right here that goes around the donut you can't deform it so that it shrinks to just a point. And then there's another loop over here going in the kind of transverse direction, which cannot be deformed away. All right, so this guy is in a way doubly not simply connected. Let me just put another arrow like this. All right. Interestingly, if I take the space and I just remove one point right there, that is simply connected. Because now that hole is in a way not a barrier. And if I have a loop, I can always kind of move in the third dimension to avoid that hole. And so any loop can actually be deformed into a point. All right. Okay. Maybe a more analogous thing to that hole, to the kind of the plane situation with a hole, you could think of space, where you remove, where you have, well, let's say you have everything in space except you remove the z-axis, right? In that case, if you have a loop that goes around this way, you cannot deform that to a point, because you're going to have this whole z-axis which forms as a barrier. All right, not simply connected. Oops. So this concept is going to be useful for us, but in real life, in mathematics, it's a super important concept as well, because this idea of deforming a loop into, being able to deform a loop into a point, or deform away a loop, helps us classify mathematical objects. So the fact that, like I said, oh, I'm sorry. If we're talking about space, this donut only has one loop that doesn't work. If we're talking about just the surface of the donut, then there's two. All right, because sorry about that. Because if we're just talking about the surface, right, this guy can't be deformed into the donut. Whereas if we're talking about including the inside of the donut, I can certainly deform that away. All right, so so I was saying, one way to classify surfaces, or to classify kind of topological objects, is by whether they have loops that deform. So the surface of a donut here, it has two loops which cannot deform, kind of two classes of loops which cannot deform into a point. And so therefore a donut is for sure different from, for example, this guy here. Oops. This guy here, which can be deformed, which only has one loop which can be deformed, which can't be deformed. So this is actually a really interesting topic in mathematics. And again, it's about, classification of in a way, geometric or topological objects. All right. So all of these definitions are needed to discuss whether vector fields are conservative or not, because again, whether a vector field is conservative or not, the criterion is going to depend on the region. All right, so let's take a look at a vector field, F, and let's do this in 3 dimensions. So let's say F is F, G, H. Those are the components of F, and each of these, of course, are functions of x, y, and z. So this is F of x, y, and z, right? That's G of x, y, and z, and this is H of x, y, and z. All right. So the question is F conservative? Oops. All right. Okay. At this moment, we have no conditions. We just want to explore what it means for F to be conservative. And if from that exploration, we're going to come up with a criterion. All right. So what if it were? So let's just explore. So I'm going to call this. Let's explore. So if it were conservative, if F were conservative, right, then what does that mean? That literally means there's a phi of xyz so that gradient phi is equal to f. All right, so that f is the gradient vector field of phi. All right, so in that case, f is equal to, let me write it like this, f is equal to fgh, right? We already kind of have established that, right? We've written f as kind of these three components, but f is also gradient phi, right? What is gradient phi? That's phi sub x, phi sub y, phi sub z, okay? And so in that case, what that means is we must have, if f is a gradient vector field, then we must have little f should be equal to phi sub x, little g should be phi sub y, and little h should be phi sub z. Okay? So nothing interesting has happened yet. We've just kind of written down just definitions here, all right, essentially. But here's where things get really interesting. Remember, that partial derivatives, it doesn't matter what order you take partial derivatives, right? Remember that phi sub x y is equal to phi sub y x. Doesn't matter what order you take them, all right? Of course, we're assuming all our functions are nice enough that this is the case, right? We've said that since the beginning of the class. So all the partial derivatives, the orders don't matter, right? So let's see. Also, phi sub yz is equal to phi sub zy, all right? And there's one more. Phi sub xz is equal to phi sub zx, okay? So this is always true, right? At least for the functions that we're working with in our class. So if this is the case, then actually let's go back up here, right? F is equal to phi sub x, g is equal to phi sub y, h is equal to phi sub z. Let's substitute that in to these three equations, all right? So every time we see a phi sub x, I'm going to replace it with f. So the first equation here, I see a phi sub x and then sub y. So I'm going to replace that with f sub y, all right? On the right-hand side, I see a phi sub y and then an x. So phi sub y is g and then x, okay? All right, next one, phi sub y and then z. Phi sub y is g, so this is g sub z. And then on the right-hand side, phi sub z is h sub y, all right? Phi sub zy is h sub y. Okay, the last one, phi sub xz, phi sub x is f, and then I'm doing phi sub xz is f sub z, all right? That should be equal to phi sub zx. Phi sub z is h, and then we're sub x, so h sub x, all right? So here's where we actually wrote down something interesting. Because the order of partials doesn't matter, we must, if our vector field is conservative, we must have these three things be true. All right, so if f is conservative, then these three must be true. All right. Okay, so this means that we actually have one criterion for considering whether a vector field is conservative, and that's that if we take a random vector field, defined by f, g, h, if f sub y is not equal to g sub x, then it's not conservative. Or if g sub z is not h sub y, not conservative. Or if f sub z is not equal to h sub x, not conservative, for sure. Because if you're conservative, these three have to be true. All right? Okay. Oh, by the way, if we are in 2 dimensions in the plane, so I've written this example with 3 variables. If we're in 2 dimensions, you just get rid of all the occurrences of z and h, right? And you would actually just have 2 criteria. So, or actually you would just have 1 criteria, right? Criterion, because this one would involve z, and that wouldn't be there anymore. This one wouldn't involve z. Okay, and from the beginning, you wouldn't have this h, you wouldn't have that phi sub z, you wouldn't have this h here. So it would only be a relationship between f sub y equals, sorry, I've been arrowing the ones that wouldn't be here. So in the plane, there would only be the condition f sub y equals g sub x. All right. Okay, in any case, we've now, just from this simple kind of observation, that partial derivatives can have any order, we know that if f is conservative, then these three things have to be true. And so if one of them is not true, definitely not conservative. All right. But that's not really that's not the ideal situation. What we would really like is a criterion that says, if this is true, then it's conservative, right? As opposed to if this is not true, then it's not conservative. All right. So as it turns out, if you're simply connected, so if the region of interest, so in other words, if we're looking at f, a vector field, f, just on a domain or a region D, right? And D is simply connected. Okay, so this is actually very critical. If it's not simply connected, this thing is not necessarily true. Then the reverse is true as well. Let me put that in quotes, reverse is true. Right? Actually, technically, we would say the converse is true. All right. In other words, if you have a vector field f, and you're in a simply connected region D, right? Your entire world is the simply connected region D. Then, if f sub y equals g sub x, and if also g sub z is equal to h sub y, and if also f sub z equals h sub x, then you're conservative. All right. So altogether. So let me put an exclamation point there. All right. That's something that we are not going to, we're not going to discuss this, but it's, if you do become a math major and you take a algebraic topology class, this would be something, or maybe a differential topology, this would be something that you'd talk about. And ultimately, it's super important because what this ultimately means is you can classify. So we've said whether a domain is simply connected or not is related to kind of the shape or topology of that domain, and that relates to classifying things in mathematics, classifying mathematical geometrical objects. And now that we've related vector fields to this, right? This means that we can actually classify mathematical objects through the existence or non-existence of certain vector fields. All right. Okay, and this is actually how we do in practice do some classifications of mathematical objects in the field of topology or geometry. Okay. In any case, altogether, if D is equal to simply connected. Oops. Then f is conservative. This statement here is the same as the statement little f. So I'm just going to copy down the three guys over there. Little f sub y equals g sub x. G sub z equals h sub y. F sub z equals h sub x. All right. Let me be a little more precise. F is conservative on D. Let me write like that. All right. So in other words, there's a function phi defined on D so that f is the gradient of phi. So let me actually just include that little note here. So this is equivalent to f is equal to gradient phi, where phi is defined on D. Right? Outside of D, we have no idea what's going on. All right, so we don't even consider that. Okay, so this is really fantastic because this means that, oh, by the way, of course, we're using the same, f is equal to capital F is equal to fg comma h, like that. Okay, so this is really great because now if you give me a vector field capital F, and we have a formula for it in terms of little f, little g, and little h, I can easily determine whether it's a conservative vector field or not just by checking these three criterion, right? If the first one is yes, if the second one is yes, if the third one is yes, then it's conservative. All right? So actually super straightforward. All you have to be able to do is take partial derivatives. Okay. So if you do see, problems on homework that ask, is this vector field? F equals whatever, right? F equals, I'm just going to make something up, x squared y z cosine x sine z y, 1 plus, sorry, not 1. Yeah, we could do 1. 1 plus x y, right? Is this guy conservative? Right? So you just, if this is the question, just calculate these partial derivatives and see if the correct ones are equal to each other, right? So f sub y is equal to x squared z, right? G sub x is equal to minus sine x sine of zy, right? Are they equal? Not equal, right? So this guy's not conservative. I guess I should always say conservative, let's say on in space, in all of space, right? We should always attach a region when we're talking about this, just to be most precise. All right, so this guy's not conservative. All right, so pretty instantaneous, pretty straightforward calculations. And again, if all three are true, then you are conservative. If we're talking about vector fields in a plane, you only have to check, again, you only have to check one condition, just this first one here. All right, so things are a little more straightforward or easy in the plane. Okay, so we've answered in a way, we've answered our main question. So the next question, of course, is if f is known to be conservative. So if we had checked, f sub y equals g sub x, g sub z equals h sub y, and f sub z equals h sub x, and it works, right? And f turns out to be conservative. How do you actually find phi, right? So if f is conservative, how would you find phi, right? How would you find the potential? Let me write it out. The potential, or let me write a potential phi, just to be most precise. Why do I say a potential? Well, because if f is equal to gradient phi, you can create, there's always more than one potential, right? So if I know f is gradient phi, then f is also gradient of phi plus the same function, phi, but just plus a constant, right? Because when I take the gradient of a constant, I get 0, all right? So just a small note, you always do have an infinite number of potential functions if you have one, all right? But normally we only need one. As long as we can find one, we're really happy. Okay, so let's answer that question just by example, and it's pretty straightforward. So how would you find it? So the answer is integrate. All right. So let's do an example. Let's do kind of a big-ish example, just so that we can see lots of features here. So let's say we have a vector field f equals y squared cos z plus y minus z cubed, comma, 2xy cos z plus x plus 2, comma, and I'm going to put this one down here, minus xy squared sine z minus 3xz squared. Okay, so this guy is so this is on R3, on the entire, on all of space, which is simply connected, so we're allowed to use our theorem, or our property up there. All right, so number one, this is conservative. All right, so if you did calculate those three identities, you would see that they actually match. But to be honest, you don't actually have to check that, because our procedure, if it works, then that means it's going to be conservative. All right. In this situation here. All right. So let's just go through this procedure. So let me just put a note. This is conservative, and you can check that yourself. All right. So this is my f. That's my g, and this is my h. Okay. All right. So f is supposed to, capital F is supposed to be, because it's conservative, it's supposed to be phi sub x, phi sub y, phi sub z. All right? So immediately what we know, we've kind of already said this, right? F is equal to phi sub x, right? So f is equal to phi sub x, right? It has to be. And also, of course, g is equal to phi sub y, h is equal to phi sub z. All right? G is equal to phi sub y, comma, h equals phi sub z. But let me start with f equals phi sub x. What is f? We're just going to copy that down. So let me switch the orders of these. So phi sub x is equal to, and I'm just going to write down the formula for f, y squared cos z plus y minus z cubed. All right? Okay, if this is the partial of phi with respect to x, if we integrate with respect to x, then we're going to get phi, right? So integrate with respect to x. Okay. All right, and this is just regular integration from one variable calculus where, did I copy this down wrong? No, looks fine. Okay, sorry. Just checking my my equations here. So when we integrate this with respect to x, right, we're thinking of z and y as constants. Okay, so in this case, it's super simple because there's no x's here. So phi is equal to, and let me emphasize, right, we're talking about three variables here. So phi of xyz is equal to, the integral here, there's no x's. So this is just a constant. So it's just all this business times x. Okay, so I'm going to write it as y squared cos z times x. Let me put the x out in front. Plus xy minus xz cubed. All right, but that's not it. Remember, when you integrate, you always have to pop out a constant. Okay, so this is plus a constant. But not just a constant as in 1 or 3 or 7, right? When we're integrating with respect to x, we're thinking of y and z are constants, as constants. So this constant here is allowed to depend on y and z, right? For example, if I had a function phi is equal to xy squared, this guy here, cos z, plus xy minus xz cubed plus, let's say, z, right? Then when I differentiate that with respect to x, the z goes away, right? And we get exactly this this guy up here. And so this c is allowed to depend on y and z, all right? So it depends on y and z. This is very, very critical. If you forget this, you're going to always get it wrong, all right? So let me emphasize that by writing c of y comma z, all right? Okay, so this means it's a little harder than we might have thought, right? We integrated to get phi, but we actually still don't know the full answer because we don't know c, right? Okay, so the rest of our kind of computation is actually just to figure out c. So the question is now, what is c of yz? All right, but the idea here is that we've made a lot of progress because initially we didn't know phi of xyz, right? So we didn't know the three variable function that we were looking for. And now we've made progress because now we don't know only a two variable function, right? So we've reduced the problem in a way from a three variable question to a two variable question. Okay. All right. So as long as we're making progress, that's good. So how do we proceed? Well, we know, like we said, let's just look at the second equation. And you don't have to look at these equations in order in practice. If it turns out, you look at the structure of f, the formula for f up here, if it looks like it might be easier to start working with g or h, do that, right? There's no kind of inherent importance in starting with starting with f. All right. So next I'm going to look at this g equals x phi y, right? So I know phi is equal to this guy up here, I've just discovered. So I know g should be equal to phi sub y. I have the formula for g, so let me calculate phi sub y from what I've gathered about phi. All right. So phi sub y is equal to, and I'm just going to take the derivative with respect to y of what I just calculated. All right. So phi sub y is 2xy cos z plus x minus 0, right? Because xz cubed, when I differentiate with respect to y, goes away, plus c sub y. All right, and let me emphasize again, That's a two-variable thing. All right. Maybe it doesn't look like I made any progress, but again, like I said, we know g, right? G was given to us in the very beginning. 2xy cos z plus x plus 2. So g is equal to 2xy cos z plus x plus 2. Okay, and again, we know that phi sub y is equal to g, right? Phi sub y equals g. So let's match the two, right? So 2xy cos z plus x plus c sub y, y sub z, that's our phi sub y, is equal to g, 2xy cos z plus x plus 2. That's our g, all right? And what will happen is, if you've done these guys correctly, is you'll have lots of cancellations. So 2xy cos z cancels with 2xy cos z. X cancels with the x, right? And so we conclude cy, y comma z is equal to 2. Okay. All right. That's going to help us find c, because now we can integrate with respect to y, right? And so what I get is c comma yz, right? If I integrate the left side with respect to y, is equal to 2y, 2y, integrating the 2 on the right hand side, and then plus another constant, let me call it k. All right, but k is not just a constant, 1, 2, 3, right? K could depend on z. Okay, because again, if I differentiate something that only has z's in it with respect to y, it goes away. Okay, so when I pop out constants, constants could depend on z. All right, so ultimately, we now have phi. So let me write down my updated phi of x, y, z is, and I'm just going to copy down what I had above up here, and with my new knowledge about capital C, right? So phi of x, y, z is xy squared cos z plus xy minus xz, and then my new information is plus 2y plus k of z. All right. Okay, and again, we've made progress. In the upper equation, we did not know c, which was a two-variable function. Now in our current situation, we don't know k, but k is only a one-variable function. So we've reduced it from 3 variables to 2 variables to now just one variable being unknown. Okay, and now you can kind of guess what's going to happen next. We're going to use the last equation, which was over here, h equals phi sub z, right? We have the formula for h right there. And so we're just going to put that together in the same way we did the previous step. Okay, so h equals phi sub z, right? H was minus xy squared sine z minus 3xz squared, right? Phi sub z is equal to, and I'm just going to differentiate what I know up here. This is minus xy squared sine z plus 0 minus 1 actually, something looks fishy. Let me scroll up and take a look up here. I think I might have copied something down wrong. I did indeed. So this z minus zx xz cubed, I copied it down wrong down here. It should be minus xz cubed here. So let me fix that. Okay, because I expect a lot of these things to actually match. Okay, so let's see. Let me fix this. So z, that looks okay, that looks okay. And then this one should be minus 3xz squared. Right? Oops, sorry. When I differentiate with respect to z, the 2y, it goes away. And then when I differentiate the k with respect to z, k is just a one variable function with respect to z, so I'm just going to call it k prime. All right. Let me emphasize of z. Okay, so h is equal to phi sub z, and so these two guys have to be equal. So minus xy squared sine z minus 3xz squared equals minus xy squared sine z minus 3xz squared plus k prime of z. All right, and again, we expect cancellations like this, right? If our thing is actually conservative, we expect this to work out. And what we see is that k prime in this particular example just turns out to be 0. All right. Okay, normally you expect it to be something in terms of z, right? If it was a more generic problem, but in this case, it turns out pretty nice. And so what does that mean? That means we can integrate both sides with respect to z, right? And that tells me k of z is equal to a constant, right? And now this is a constant, just a literal constant. I guess we called it last one capital C, so let me call this one little c, right? And this is actually a literal constant, actual constant. Because the only variable now is z, and so constants with respect to just a z is just constants. All right, so now altogether, we know that phi of xyz is equal to xy squared cos z plus xy minus xz cubed plus 2y, and then our newly discovered k of z, which is just a constant. All right, so this guy here is going to form the potentials for our vector field, right? And gradient phi is equal to capital F. Okay, so normally the questions will be find a potential for capital F, and of course, to make your life simpler, you know, there's going to be a constant here. Just let c equal 0 is convenient. For a vector field, a potential. All right, so if you want a potential, just let that c be 0, and things will look a little cleaner. Okay. All right, so a little tedious, but the good news is it's super straightforward. The procedure is super straightforward. If we had asked the same question in the plane, it's much more straightforward in that there's only f and g, right? There's only 2 coordinates, and so you don't have to do as many steps. But the steps are the same. It's the same same idea. All right. Okay. So essentially, we have a decently satisfactory answer to when a vector field is conservative, and if it is conservative, how to find the potential, right? And again, this only works on a simply connected domain, for our class at least. If you're not in a simply connected domain, so if we're talking about a vector field, so one example of this that we'll see in the future is where we look at vector fields f that are not defined at a particular point. So if I look at, for example, f equals a radial vector field. So let's say, remember our vector field R, x comma y. Let's just do this in the plane, just for simplicity. R is equal to x comma y. If I look at this vector field here, this guy is not defined at the origin, right? Because we're dividing here by r, and so r would be 0 at the origin, because this is r is distance to the origin, and so this vector field is not defined here. And so remember, this was sorry, I didn't want radial. I wanted did we have a name for it? No, I guess not. Sorry, I didn't want r. Let me put the. I want minus. I wanted a rotational vector field. But this bottom is the same. I want it to be the distance to the origin. So what happens is this guy looks like this, right? And the deal is there's a hole in the middle, right? In that we cannot define f there. So if we were to study this vector field, our region would be the plane minus the origin, right? We're just simply not allowed to look at the origin in consideration with this vector field because it's not defined there. And so this guy here is not simply connected. So we would not be allowed to use our criteria for vector fields for conservative vector fields in this situation. All right. Okay. Why is that important? Well, because if you actually try to use the criterion, right? So in this case, it would be f sub y equals g sub x. It would actually be true. True, but f is not conservative. Right. So this shows us a literal example where we absolutely need the simply connectedness. All right. And we know f is not conservative because we said in our lecture about vector fields that it just can't be, right? How can this be a potential if it was the gradient of some potential function, then starting here, if I travel around, right, my value of my function gets bigger and bigger and bigger. And when I come back, it needs to be a bigger value. And we can't have functions with multiple values. All right, so this guy is definitely not conservative. Okay, in any case, though, we do have, I guess, a decent criterion for when vector fields are conservative, and if they are, how to find them. Let's write down now something really important, fundamental theorem, or at least this is what our book calls it, for of line integrals. So we're going to be studying line integrals quite a bit next week. So this theorem is going to be really useful for us. Okay, if f is conservative, let's say on some domain D, all right, then integral c f dot t ds. So this is a fundamental theorem of line integrals, right? So this is my line integral in question, all right? Is actually going to be super simple. So let me not just write down the statement of the theorem. Let me actually prove this. Let me just go through this computation because it's actually fairly straightforward, and we'll see the final line will be really nice. All right. So let's just actually do the computation, and we'll see what the theorem should be, or what the theorem is. So integral f dot tds. Remember, this is you can think of this as work, right? This line integral quantity here, and we're kind of calculating the work as we move from the start point of C to the end point of C. All right. So I guess I should let me draw a small picture here. So let's say this is C. Okay. This works whether you're in space or in the plane. It doesn't matter. All right. Let's say the start point is, again, when we talk about line integrals, we always have a direction, right? Because we have this t here, and the tangent, unit tangent always has a direction, okay? So we're talking about a curve with a direction included as part of its kind of core information. Okay, so let's say we start at capital A and we end at capital B. Okay, now how do we actually calculate line integrals? Well, we parameterize, right? So let's say R of t is a parameterization. That allows us to calculate this line integral, right? So obviously we would like, R to not repeat itself, right? To move forward and backwards and forwards and backwards or anything like that, right? We want nice behavior here. We would like R to be one-to-one, right? Okay, so R is a parameterization. I'm not going to write that, but we've talked about that in the past. So say R is a parameterization where, let's say R of t equals little a is equal to capital A. R of t equals little b is equal to capital B. All right. I want to write this down because we're going to actually calculate this line integral. All right. So what is it? So this is going to be integral first step is I'm just going to use the fact that I'm conservative, right? F is conservative literally means f is the gradient of some function phi. Okay, so this is the first thing that we definitely know. This is equal to this. And then now we're going to use our parameterization. This is equal to integral, and I'm going to write this whole thing out, gradient of phi, and just to emphasize, we're converting to calculation of a line integral. So this is phi of x, and x depends on t, right? That's what my r is, y of t, z of t, all right? R prime of t dt. Okay, and this is from a to b. So remember the last section, we said that when you integrate, when you calculate a line integral of a vector field, it actually turns out fairly simple. There's no speed term, right? Absolute value of r prime. Okay, now this looks absolutely terrible, but let's rewrite this down here. This is, what is gradient phi? I think I need a little more space. So this is a to b. What is gradient phi? Gradient phi is phi sub x. So let me write it in terms of partials. Phi sub x phi dx, right? And then comma phi sub y and comma phi sub z. All right, and this is all x of t, y of at x of t, y of t, z of t. So everything is in terms of t, ultimately. All right, and then what is r prime? R prime is dx dt, dy dt, dz dt. All right, and then dt. And here's a dot product. All right, so all I've done is I've written out the definition of phi, of gradient phi, and I've written out the definition of r prime. Okay, and sorry, I should emphasize that's a dot product right there. So that we're actually, just to emphasize, we're actually integrating, that's a regular one variable calculus integral of a function with variable t. Okay, so let's write this out. This is a, b, and I'm just going to take the dot product. This is d phi dx dx dt plus d phi dy dy dt plus d phi dz dz dt. Right? And all that happened is I took the dot product, right? This times this, plus that times that, plus that times that. Okay. Right. However, hopefully we know, we recognize this expression here. That's just a chain rule expression. That's just a to b ddt of phi of x of t, y of t, z of t dt. Right? Literally the chain rule, right? If you take the chain rule with respect to ddt of phi of this business, you literally get that guy upstairs. Okay, why do I care about that? Well, let me put the brackets like this. I am taking the derivative, I'm taking the integral of a derivative. So the regular one variable calculus, fundamental theorem of calculus applies, right? This is just one variable calculus at this moment. It's a function of t here. So this is actually phi of x of the right endpoint, which is b, comma y of b, comma z of b, minus phi of x of a, y of a, z of a. All right. Okay, but what is that? Well, we said our parameterization had r of little a is equal to capital A, r of little b is equal to capital B, right? So that means our start point x of a, y of a, comma z of a is capital A, and our endpoint xb, comma yb, comma zb is our endpoint capital B. So this is actually equal to phi of b minus phi of a. Okay. All right, so ultimately, let me write down the conclusion here. So integral f dot t ds over my curve is actually equal to phi of capital B minus phi of capital A, right? Where B, A is equal to start of C. Let me put that in quotes. That's not completely mathematical there. B is equal to end of C. Okay. All right, and you can, again, it's really important to always note this. You can see that uh, these things have a direction, again, in that your t has a direction, right? And on the right-hand side, you can see that there's a direction because it's the end point minus the start point. So if we were looking in the opposite direction, if we were traveling in the opposite direction, it would be phi of A minus phi of B. And we would get negative of this answer here, right? And that makes sense because, again, in terms of work, right? If you go one direction, you do positive work. In the other direction, it would be negative work. Okay, so why is this called the fundamental theorem of line integrals? Well, we use the fundamental theorem of calculus, so that kind of makes sense. But another way to understand this is instead of writing f dot t ds, I can write this as gradient phi dot t ds on the left-hand side, and then the same thing on the right-hand side. All right, so this makes more sense in terms of the terminology fundamental theorem, because what is the fundamental theorem of calculus? And this is really important because we're going to have many fundamental theorem of calculuses in the next week. And if you don't kind of think of them that way, it's going to be a lot harder to learn the material. So why do we understand this as a fundamental theorem of calculus, or why does it make sense to use that name just from this expression? Well, fundamental theorem of calculus says if I integrate a derivative, right, my answer should be something where I look at the endpoints of my original function, but with no derivatives, right? So we actually saw that up here, right? When I integrated here, ddt of something, of phi, right? What did I get at as the output? I looked at the endpoints, and I'm not taking any derivatives any longer. Okay, so here that's exactly what I see. On the left-hand side, I have a derivative, right? On the right-hand side, the derivatives are gone. Okay. On the left-hand side, I'm looking at an entire curve. And on the right-hand side, I'm looking at the boundary of the curve, which is just the two endpoints. All right. That's what the fundamental theorem of calculus is about, right? And let me just emphasize that by writing the fundamental theorem of calculus again, or at least one version of the fundamental theorem of calculus from calculus. Right? We literally see the same thing from one variable calculus. Here we have a derivative. Here we have a line segment, right? Or let me call it a interval. On the right-hand side, notice no derivative, and also endpoints or boundary of the interval, which is the endpoint. All right, so this is the pattern for the fundamental theorem of calculus. And again, I'm emphasizing it now because we're going to be seeing many different fundamental theorem of calculuses very soon. And it's really good to kind of have this core understanding of what it means. All right, this is great. This is great because it means that if I have a conservative vector field, I can do line integrals really easily, right? If I have a conservative vector field and I want to do a line integral from here to calculate the work, right? From work done from A to B by that vector field, right? As I travel from A to B, and let's say f is equal to gradient phi, then instantly I know the answer, right? The work done, the work done is instantaneously, I know it's phi of B minus phi of A. All right. So super powerful. Okay. So for example, in our previous example where we had that horrible looking vector field, f equals what was it? Y squared cos z y plus y minus z cubed, right? Comma 2xy cos z plus x plus 2, comma, etc. Right? If you wanted to integrate this, right? So let's say I ask you to integrate it from over a curve. Let me actually give a concrete curve. Over a curve, let's say over a helix, right? Over C, where C is a helix, right? Like this, starting here and ending there, right? What is this going to be, right? You would have to, without any kind of knowledge of conservative vector fields, you would have to parameterize this curve, right? This helix. You would have to take the dot product, and these, again, this F is kind of nasty, right? Your T is going to consist of cosines and sines and stuff because this is a helix, so that's already going to be unpleasant when you do your integral, right? It's going to be a huge mess. But now I know capital F is conservative, right? We've actually found the potential. And so immediately I know the answer is phi of B minus phi of A, where if this is B, that is A, right? I instantly get the answer. So how much work did I have to do? I had to find phi, of course, right? But oftentimes that's easier than doing some horrible integral here, particularly if your curve is really ugly. All right. Okay, so this is one kind of useful application here. Another really, really important feature here, and this is super important in terms of physics, is path independence. All right. So first of all, what does path independence mean? Path independence means if I have, I'm just going to draw kind of a picture version here. If I have point of interest A, point of interest B, I have curve 1 going from A to B, let me call that C1. I have curve 2 going from A to B in a different path, right? Path independence essentially is saying that it doesn't matter what path I take, I'm going to have the same work relative, of course, we're talking about vector fields this whole section. We have some vector field F here, right? So path independence in this context means it doesn't matter what path I take, I do the same amount of work, okay? So integral C1 F dot T ds equals C2 F dot T ds, no matter what path I take, no matter what C1 is in C2, as long as they have the same endpoints. Okay, so path independence means this equality is true no matter what paths C1 and C2 are, as long as they have the same endpoints. Okay, the same start point and the same end point. Let me write same start and end points. Okay, so we really, really like path independence, and we see path because, well, one practical application for that we'll see in our class is if we have a vector field that has path independence, right, then if I ask you to calculate the work along this path, right, alternatively, you could say, okay, I know this guy's path independence. I'm not going to do this horrible path here because it's too hard to work with. It's too hard to parameterize. I'm instead going to do this path right there, right? And I know I'm going to get the same answer because my vector field has this path independence property. Okay, so calculating again with this horrible path up here, right? Calculating work done by my vector field is too hard. So alternatively, I calculate the work done over a nice simple path. Okay, so if I have a vector field that satisfies path independence, I can do this. If it doesn't satisfy path independence, I cannot do this. All right. If I just close my eyes and write down a vector field by random, it's not going to be path independent. Okay. So a natural question is, when is a vector field path independent, right? Well, we've actually answered that question already, partially, in that, well, we have our fundamental theorem up here, right? Or I guess let's do the F version. We have our fundamental theorem right there, and this literally is telling us conservative vector fields are path independent, right? Because no matter what C was, my answer is phi of B minus phi of A. And that neither of the right-hand side depends on how C moved from A to B, right? It only depends on the endpoints. So conservative vector fields are path independent. Okay, that's actually super important. Okay, both in math and in physics. How in physics? Well, a lot of the vector fields you encounter in physics are conservative. Gravity, the gravitational vector field, we actually talked about this when we first gave that example. That's conservative, right? And if you've taken physics, you know that it is path independent because you know that from physics class, you know that work done by gravity only depends on actually your initial height and your final height, right? So it only depends on your position, not how you got from your initial height to your final height. Okay. And actually, now that I think about it, I think in I think it was in homework 1, we had a problem about finding the work done as some object slid down an incline, right? And if you looked at the answer there a little carefully, you'll have noticed that it actually the work done depended only on the height that the object traveled, the vertical distance the object traveled, right? So that is kind of a result or a consequence of the fact that gravity is a conservative vector field. Okay, so we love conservative vector fields even more now, because that means, again, if I have a vector field that is conservative and, I'm asked to figure out the work done as I travel from here to here along that horrible path, I just used a path of my choice instead, and I do the same calculation. And presumably it would be a lot easier because I get to choose the path. All right, so that's one direction in terms of the path independence question, right? Conservative vector fields are path independent, right? But in fact, there's a theorem that goes the other way. If R is open and connected, all right? So open means, well, not closed. So it's kind of the two-dimensional or three-dimensional version of an interval that looks like that, right? As opposed to something that looks like that or something that looks like that. Okay, we're not going to dwell on it too precisely, but that's the idea. Okay, so let's see. An example of an open region would be x squared plus y squared less than 4, right? An example of a region which is not open is x squared plus y squared less than or equal to 4. Okay. All right, similar to the interval situation where this is an open interval, right? And this is not an open interval. Okay. All right. Maybe I should say more precisely mathematically, a region is open if for every point in the region there's a tiny little ball around that point that entirely lives in the region. Okay, so that doesn't work for this case because on the boundary right there, there's no tiny little ball that lives entirely in the region. All right. Okay, in any case, if R is open and connected, and if integral f dot t ds is independent of path, then f is conservative. Okay. So this kind of fills in the opposite direction of the statement upstairs, which said if you're conservative, then you're path independent. Now we know if you're path independent, then you're conservative under this condition that we're interested only in our open connected region. All right. All right. Why would this be true? Actually, it's true pretty easily, because if your path, oh sorry, I should put a C here. If you're path independent, then that means we know phi of b minus phi of a is equal to integral c f dot t ds, right? If it were to be conservative, right? So that means that we can actually figure out phi by integration, right? So if I have a here and I have b here, I can just say, okay, phi of a is equal to 0. All right, and then what should phi of b be? I can actually construct it. So phi of b should be equal to integral c f dot t ds, where c is any path from a to b. Right? Let me write it like this: phi of b minus phi of a. This is equal to 0. I've chosen phi of a to be 0. Right? And so that gives me a definition for what phi of b should be. All right, and so this constructs a function for me, and if I check it, gradient phi is indeed equal to f. All right, and this whole procedure works because of path independence, right? Because it doesn't matter what path I take from here to here, my integral will be the same. Okay, if this were not the case, then there's problems with this definition, in that it's not going to be well defined. All right? Because then if you take different paths, you get different phi of b's, which definitely is not cool. All right. Finally, let's take this very special case of closed curves. All right, so far we've been talking about this C here, right? We've been talking about endpoints A and B, right? But now let's restrict ourselves to loops, all right? So C is a closed curve. It loops back on itself. So the start point is the same as the end point. All right, so if C is a, I'm just going to write it kind of colloquially, is a loop, right? Then if F is conservative, then integral over C f dot t ds, what is that? Well, if you're conservative, this is equal to phi of start, or phi of end, minus phi of start. Right? Whatever phi is, we know there exists a phi because this guy's conservative, right? Let me write just to kind of describe phi. If f equals gradient phi, right, is equal to phi of n minus phi of start. But C is a loop, so phi of n minus phi of start is 0. So that's equal to 0. All right. So in the special case of a conservative vector field, integrating over a loop, our answer is always 0. All right. There's actually a special notation for line integrals when we're integrating over a loop, and that's where we put a little kind of loop there. Right. That indicates we're integrating over a curve that closes up on itself. All right. Okay, so ultimately our conclusion is conservative. That tells us that integrals over loops, the work integrals, is equal to 0. Okay, and that actually makes sense. Let's say in the example of, let's say gravity, right? If I take an object, I move it around, and then it ends up at the end back where it started, right? I move it back to where it started. How much work has gravity done overall? It's done no work, right? Because the object stayed in the same location. All right. So again, this feature is actually super important. We will be talking about, we will be wanting to work with conservative vector fields. Well, again, like we said, in physics and in future sections. they always make our lives a lot simpler. Okay, by the way, I've tried to be a little consistent in my notation. I've always used for the work integral f dot t, or for the vector line integral. I always call it a work integral just to keep it more grounded in terms of how to interpret it, right? So I've always used the work integral written like this, just to keep things consistent. But just as a quick note, remember this is the same as this, right? Just notation wise. And this is the same as this guy, f dx plus g dy plus h dz. All of these are the same notation. And I think the book really likes to use this notation here. And a lot of physics classes like to use that as well. So make sure, again, you're comfortable with all the different forms of the notation. All right, so next week we'll put a lot of this stuff to use. And we'll talk about our really, really big theorems for this class.